This is Fiat Lux IV, the fourth episode in the trilogy of talks on the nature of light, hence Fiat Lux, Let There Be Light. But you don't need to have seen the previous three in order to make sense of this one. This is a standalone talk about the nature of light and colour in the cosmos. So I hope to convince you that colour is perhaps not quite what you thought it was. So I'll give a brief introduction, and then we'll be looking at how we as humans perceive colour and how we quantify colour in order to make sense of it. And then we'll be looking at the colours of stars and the colours of nebulae and why they differ from each other, what's the physics behind that. And then briefly a little look at spectroscopy and going beyond the visible spectrum. And then I'll have a quick summary at the end. So, what is colour? It's a bit like what is time. If you ask people what is time, everybody knows what time is, but try and define it without using the word or any other time-related word. It's difficult. The same with colour. Trying to define colour. How would you define colour to a blind person? How would you define colour to an alien who doesn't see colours the way we do? So you could say, even, is colour real, or is it just a human perception? Is it real, or is it just a pigment of your imagination, as they say? So, okay, we've all seen colour. We're all, if I remember rightly, none of us are colourblind, so we all see colours in pretty much the same way, we assume, and we admire the beautiful colours of a rainbow. So the question is, why do we have colour vision? Why do humans have colour vision? Of course, if we didn't have colour vision, rainbows would be really boring. But you could argue that we have colour vision in order to make sense of, for instance, a lot of people say, well, it helps you decide whether or not to eat a fruit or not because it tells you if the fruit is ripe. So here we have three fruits. Any idea which ones are ripe and which ones aren't? Any guesses? Okay, as soon as you have colour vision, it's pretty obvious which is the fruit that you need to eat or should be eating and which is the fruit you ought to eat. It's not necessarily the fruit in front of you. It might be a tree a long distance away, and you might decide, I'm not going to walk to that tree because none of the fruit there is ripe. I'll walk to a different tree. So there's an evolutionary advantage to be able to see ripe fruit. Other people have different ideas as to where colour vision came from in terms of the evolutionary drive. I think colour vision is a consequence of us needing to read maps. And so you can see that trying to make sense of that is rather tricky until you put the colour back in, and then it all makes sense. So maybe that's what evolution is driving us towards. So how do we perceive colour? Well, yes, you know about the human eye. You know that light hits the retina, and the retina has got a whole set of photoreceptors in it. They come in sets of what you would naively think of as red, green, blue receptors, and these receptors turn the light into a chemical reaction into an electrical signal, which then ends up getting piped to the brain via the optic nerve. So you might think of an eye as being sort of like a camera. It has different colour receptors which pick up colour signals, and they get fed to the brain to be interpreted. But if you think of comparing it with a colour camera, for instance, the chip on a colour camera is monochrome but has a whole load of filters on the front so that each pixel effectively picks up only the green light or only the red or only the blue. This particular arrangement of coloured filters on a camera is typically called a Bayer grid. A lot of different manufacturers use that idea. And if we look at the sensitivity of the red, green and blue filters in a colour camera, we see that roughly speaking, not quite, but roughly speaking, each of the red and the green and the blue covers about a third of the spectrum. And they overlap with each other, not surprisingly, so that any particular wavelength between 400 nanometers and 700 nanometers from blue to red, they overlap such that no particular wavelength gets missed. And of course, at some wavelengths, you get a signal from two different color receptors of the camera. But the human eye is a little different in that if you think that's how your color vision works in terms of blue, green, and red, it's actually rather different for the human eye. Blue is sitting right out there towards the blue end of the spectrum, and notice that red and green are actually very close together, which seems at first quite surprising. You look at that and you think, well, nature hasn't done a very good job of spacing out the color receptors' responses in order to give you color vision over the whole spectrum. In fact, when you look at red, although we think of that as a red receptor perhaps, notice that it actually picks up a signal all the way from 700 nanometers Actually, all the way to 400. Even blue fires the red receptor. Notice that in a spectrum, if you remember your spectrum, red, orange, yellow, green, blue, indigo, violet, the spectrum doesn't go from red to blue. The spectrum goes from red to violet. We start to pick up just the hint of a little bit of reddening coming in to that end. Even though red is at this end of the spectrum, our perception is that there's a little bit of red coming in, making the end of the spectrum violet rather than blue. And that's because the red receptors actually are still firing, even at this end of the spectrum, whereas you would expect most of it to be at the other end. Notice that not only is it a misnomer to call it a red receptor, notice it doesn't even peak in the red. Not only does it cover all colors, it actually peaks in the green, and it's right next door to the green. So biologists do not refer to these photoreceptors as red, green, and blue in the sense that we think of red, green, and blue in a camera. They refer to the photoreceptors as the short wave, the medium wave, and the long wave. In other words, which bit of the electromagnetic spectrum are they sensitive to? Simply because calling them red, green, and blue gives us the wrong impression as to what the sensitivity actually is. Just as a little bit of a diversion, because this is of interest to astronomers, the rods in your eye, the sensitive photoreceptors that are not sensitive to color, the rods work in nighttime and don't give us color vision at night. The rods are sensitive to low light levels, whereas the cones will fail once the light levels have dropped. And so the rods actually are sensitive to this end of the spectrum, which is why astronomers use red light, and that's why photographers also use red light, to save their night vision, because if you use red light, your rods do not care if you're illuminating things with red, so your cones then work if the red light is bright enough, but the rods aren't sensitive to the red light, so your night vision is preserved if you use a red light torch at night. So we have three sets of receptors. We should call them short wave, medium wave, and long wave, but let's just call them red, green, blue for short, even though we know that's not quite right. We have three sets of color receptors, so we have trichromatic vision. But some animals have more. For instance, there's an animal with 12 sets of photoreceptors in its eye, covering, notice, not only the visible spectrum, one of them actually goes into the infrared, and actually quite a few of them go into the ultraviolet as well. Any idea which animal needs 12 sets of photoreceptors to live? Any guesses? Very, very close. It's a mantis shrimp, that particular one. I haven't seen what the actual set is for an octopus, but yes, a lot of marine mammals have more receptors than you might think. Clearly, these are animals that live fairly close to the surface. If you're very deep, everything is blue, so there's no need to have color vision. But yes, there are certain animals that have far more complex color vision than we do. So it's difficult to work out if you've got 12 sets of receptors that are all firing and sending signals to the brain. You start to wonder, well, how many colors can a mantis shrimp see? Unfortunately, we can't ask to find out what sort of colors it thinks it's perceiving. So 3 sets for us, but how did we end up with 3 sets of color receptors in human vision? Well, our color vision has actually evolved over some 100 million years or so, ever since we were a small furry mammal. If you go back to when dinosaurs ruled the earth, we were nocturnal because we were sort of a little shrew-like creature which lived at night, or at least came out at night when dinosaurs were stomping around during the day. Once the dinosaurs were wiped out, those animals could become diurnal rather than nocturnal. So when we were nocturnal, there was no need for color vision because we only came out at night. But in the intervening 100 million years or so, or 60 million years since the dinosaurs were wiped out, genetic mutation has restored our color vision. It's thought that we had color vision before the dinosaurs and before we were this particular pre-primate here, and basically genetic mutation since we were nocturnal has brought that color vision back again. So of course I'm not saying that Homo sapien is the ultimate end of evolution. Who knows where evolution is going to take us when we get beyond that end of the line, as it were. If we ask why visible rather than anything else, well, not surprisingly, the sun dishes out a lot of visible light. We'll see why shortly. but also it's a question of the atmosphere transparency. So the atmosphere blocks an awful lot of X-ray and ultraviolet, quite a lot of infrared, and some of the radio. So the amount of light that actually gets down to ground level is a little window here in the visible part of the spectrum, and there's also quite a large window in the radio. But at wavelengths of a meter or so, it's difficult to believe how any particular organism can develop sensitivity to radio waves. And of course, they're not particularly intense compared to the intensity of light waves. So not surprisingly, if we want to know how the universe works, we build telescopes on the ground that make use of this particular range of wavelengths. If we want to find out what's going on in the ultraviolet and X-ray and in the infrared, then we basically have to have space-based telescopes, such as these mentioned up here. James Webb, Spitzer and Herschel have been working in the infrared for quite a while, at least Spitzer and Herschel have, and there's also a number that have been working in the UV. Of course, that doesn't stop us putting a visible light telescope up in orbit, but strictly speaking, we don't need to, in the sense that the light does actually arrive at ground level. But if we return to this idea of photoreceptors in the eye being sort of red, green, blue, in the sense that their wavelength doesn't quite match to a camera, but we can still think of them as being red, green, blue photoreceptors. Let's just ignore the rods for the moment and just think about the colors. If we look in more detail at what's actually going on, we find those photoreceptors actually account for only a small number of the cells in the back of the eye. The retina is actually made of rods and cones at the back here, but also there's a humongous number of neurons. So in other words, we think of the brain as being a whole load of neurons that are processing the signals from our eyes, but actually a lot of the processing is actually done inside the eye, not by the brain. So in that sense, the eye is not simply a passive device for catching photons and then sending the information to the brain to be interpreted. In a sense, the eye does some of the interpretation, because neurons here are not simply connected to one photocell, not one photoreceptor. A neuron can be connected to multiple cells, and so it takes signals from more than one cell to decide what signal actually gets sent to the brain. So if we compare that with a camera, where we have red, green, blue pixels on the camera, and the red, green, blue signals that are coming off the chip effectively are dealt with by the camera circuitry, and not an awful lot is done to those before the information is plonked onto your SD card in the camera. Yes, they can change a little bit. The amount of red might go up, the amount of green might go down. There's often a little bit of color balance adjustment of the signals, but essentially the red and the green and the blue that were the original pixels of the image end up as the red and the green and the blue pixels on the, whatever it is, the JPEG or the TIFF image that now sits on your SD card. But the eye is very different. It might start with a red, green, blue signal coming from the photoreceptors. So the starting point might be the same, but what happens next is very different in the eye compared to what's happening in a camera. Effectively, the neurons in the back of the eye act as a little neural net, and each of the red, green, blue signals gets sent to multiple neurons, such that the signal that eventually gets sent to the brain, which of course is yet another huge neural network in its own right, these signals are not simply the red, green, blue. The optic nerve does not carry red, green, blue information to the brain to interpret what color are you looking at. The neurons of the eye effectively give you mixtures of colors. It might tell you, is the red bigger than the green? It might be, this is the difference between the blue and the red, for instance. There could be different signals, there could be averages, and so trying to work out exactly what is being fed to the brain is, of course, a question of physiology. If we understood exactly what those neurons were doing, it would be a little easier to make sense of color vision. So the fact that red, green, blue are not simply signals sent to the brain accounts for some oddities when we look at our color vision. Now, I can't remember offhand. Have I showed you this before?
I think I've seen it.
Yeah, I've occasionally incorporated this into other talks, and I can't remember if I've explicitly shown you. Let me pretend that you haven't seen this before. So there's a couple of sort of Rubik's cubes. On the left-hand side, I'm interested in the color tiles on the top face of the cube. So how many of them on this side here, on the left-hand side, on the top face, how many of them are blue? 4. Okay, any other takers to 4? No? On the right hand, how many of these tiles are yellow?
7.
Any other takers? So you think there were 4 blue on the left and 7 yellow on the right. Are you prepared to put good money on that? Because it is a surprise to most people, and even though I've seen this 20 times, it's still a surprise to me that if you take all of the other pixels away, other than the pixels comprising those 4 tiles there and these 7 tiles there, if you take all the other pixels away, you see what the true color of those tiles actually are. And the result is probably, I hope, surprising, because if you take all the other pixels away, they're actually the same color. They're actually both gray. It looks like a cheat, because no matter how many times you look at this, you say, well, surely you're doing something to those tiles when you're taking the other pixels away. No, absolutely. If you want to go to this web page and check it out for yourself, you can convince yourself it is absolutely true. I've taken a screen grab of that image and checked pixel by pixel. They are absolutely, that color is absolutely the same as that color. The blue on the left is the same color as the yellow on the right. Your brain is telling you the left one is blue. Your brain is telling you the right one is yellow. I should say a combination of your eye and brain is telling you that. And that's simply because the neurons in your eye and ultimately your brain is telling you that that is a little bit bluer than the rest of the background, which is, of course, deliberately yellow on the left and blue on the right. So your brain is telling you about differences, not about absolutes, because your brain thinks that's what you need to know. If you've got a book and you're reading a book and the page is white, and you go from a darkened room out into the sunshine, the color of that page will change. But your brain says it's still the same book. So even though the light is actually changing and the color is changing, your brain works out that's not because the book has changed, it's only because the outside light has changed, and therefore I won't give you extraneous information. Your brain is trying to do you a favor and giving you only the information it thinks you want. This is true not just of colors, whilst we're on the same topic, it's also true of simply intensities. If you look at this one, there's a square there labeled A and a square labeled B, and you can ask, well, which one appears to be the brighter? This is not specifically color, but it's still related to how the neurons are processing information that comes from your eyes. When you look at that gray, not the letter itself, but the square on which the letter resides, you can be pretty convinced that that square is darker than that square. However, if I block out some of the extraneous pixels, now what can you see in terms of the grayness of that one, which is exactly the same as the grayness of this rectangle and the grayness of the left-hand rectangle, the masks that I've introduced? Notice that it's exactly the same for both of those tiles. Those tiles are the same shade of gray. If I take those masks away, you know with absolute certainty that the square labeled A and the square labeled B are the same shade of gray. But it's impossible to get your brain to recognize that. Your brain is telling you, yeah, your eyes are registering a certain intensity, but what's actually going on, your brain is overriding the intensity information and telling you what you think is going on, because your brain is thinking, well, that's obviously a chessboard, and obviously these ones here are darker than these ones here. So you cannot rely on anything your eyes are telling you, either in terms of color or indeed in terms of intensity, because of the image processing, because of the signal processing that the neurons in your eye are doing on receiving signals from the photoreceptors. So human vision is unreliable. That's perhaps not surprising. But how do we quantify color? Well, if we ask a physicist to quantify color, the knee-jerk reaction is a spectrum. And for those of a certain age, a spectrum means that particular device there. But of course, for the rest of us, it means taking white light and spreading it out into its colors. So here's Newton in the 1660s trying to reproduce the front cover of the Dark Side of the Moon album there. So Newton, of course, established that white light is composed of many colors, and he did a lot of work on looking at the spectrum and recombining colors, etc. And we know that whenever glass prisms are used, or indeed diffraction gratings, but I'm not going to go down that route today. Whenever light passes through a glass prism or another optical instrument, then its wave nature is revealed. And we all know about the amplitudes of waves and the wavelength. And of course, in the visible part of the spectrum, then people will disagree as to exactly what the visible spectrum is, because every human is slightly different, but roughly speaking, the violet end of the spectrum is at about 400 nanometers and the red end at about 700 nanometers. But those colors in the spectrum, the so-called spectral colors, are not all the colors that exist. For instance, where is beige? Where is brown? They don't occur in the spectrum. So the rainbow of all colors is not the rainbow of all colors, it's the rainbow of some colors, the spectral colors. If we want to show all colors, then we need more than simply a line that goes from blue to violet to red, or from red to blue to violet. And there are different ways of quantifying it. I'm not going to go through all of the mathematical detail, but it is possible to plot colors on a two-dimensional plot in which we have a chance of now expressing all the colors that are possible. And that was decided by a particular group called the CIE up there at the top there. So all colors can be quantified and plotted in a so-called color plane. And in this talk, I am not going to discuss what the axes actually are. The axes are mathematical quantities which allow you to plot any color in a particular two-dimensional plane. Different intensities of that color will be a third dimension, which we're not going to be looking at. So spectral colors actually run around the outside of that particular color space. Notice that it's very nonlinear. Notice that on the right-hand side, we've got a relatively small space between 700 and 600 nanometers, but the greens get stretched out so that the green actually occupies a large number of whatever you want to call it, a large number of real estate, a large amount of real estate at the top of the diagram. And again, if you look in the bottom left there, all of the blues from 400 to 480 are squeezed into a relatively small part of that map. One of the reasons the mapping is done this way is because it reflects the color sensitivity of human vision. In other words, human vision is not particularly good at separating lots of closely spaced reds. It's also not particularly good at separating lots of closely spaced blues. It's great at separating a lot of greens. Remember the color receptors in the eye? Red and green are quite close together, which gives you very good discrimination in the middle part of the spectrum. So that's why they're spaced out like this. But if we think of a display, whether that be a monitor display or a projector or any other device such as your phone or a TV, etc., you can't necessarily display every conceivable color on a particular device. A device has technological limitations. And in fact, there's only a particular range, a so-called gamut, in which the colors can be displayed. So for instance, on this particular device, it might be that we can only reliably display colors in this particular range of the whole color space. It might be that we can't actually ask the projector to generate a color outside that triangle. And that's because the device, whether it be the phone screen or whether it be the projector screen, has a particular set of pixels like red, green, and blue, which get mixed together to make colors. And if you mix those three colors together, you get any arbitrary color you like inside that triangle by mixing certain amounts of red, certain amounts of green, and certain amounts of blue. But no mixture of those three red, green, blue primaries will generate a color outside the triangle. So in other words, this particular projector is incapable of generating true colors out here. Notice that outside the triangle to the left, there's a huge region which all looks sort of the same color. That's because the projector is no good at actually discriminating those colors. Hopefully, you will be able to make out distinct colors inside that triangle, and each point inside that triangle corresponds to a distinctly different color. But in the bottom right, for instance, these purples, it's quite possible all the purples look the same. It's quite possible in the top left, all the greens look the same. And any particular device will have a different set of red, green, blue markers that define the primaries to generate its color gamut. That's why when you display a particular image on a particular monitor and then move to a different computer, which is made with a different set of red, green, blue pixels or phosphors, it doesn't necessarily look the same because you have a limited range of colors that can be reproduced. So let's have a think about how the cosmos works with colors. Colors of stars. Where do the colors of stars fit? If this is the arrangement of all colors in this so-called color space, where do the stars fit? And you might think, well, if you go out on a starry night, most of the stars look fairly white. Okay, true, because your color vision is not very good at night. If you get a pair of binoculars or a telescope, you'll start to see colors in the various objects that are out there. The more light that enters your eye, the more you will perceive color. But where will the color stars actually appear in this diagram? It's perhaps much more restrictive than you first appreciate. All stars will fall on that line. In other words, you might think, well, there'll be some red stars and some green stars and some blue stars, and they'll be all over the place. Nope, stars will only appear on that particular line. Cool stars will appear on the right-hand side, and very hot stars will appear on the left. Even really, really, really hot ones will still go no further than that sort of end of the line labeled hot stars. And that's because stars can't be just arbitrary color, they must obey the laws of physics. If you take a material and heat it up, so imagine we've supplied some heat to the right-hand side of this metal bar, and some of that heat is conducted down the bar, so there's a temperature gradient from one end to the other. And the right-hand end is virtually white hot, and then it goes a sort of yellow, then it goes a little orange, and then we get a bit of red hot bar, and then we can't see any particular color to the left of that. It is still producing radiation, but that radiation will be in the infrared. So every bit of this bar will be radiating some light, but not all of it in the visible part of the spectrum. This is called blackbody radiation, where it's the radiation produced simply because the object is warm, is hot, and there's a certain amount of energy within the material. We're not going to worry about the details of the atomic nature of motions and vibrations, etc., within the material. But physics tells us that the spectrum of radiation coming from any particular point will be a particular function of the temperature. This is called blackbody radiation. And this is nicely indicated by this set of animations available as an educational resource here. If we think of what is going on with a temperature of an object, it, strictly speaking, doesn't actually matter what the object is, as long as it's a black body. In other words, as long as it emits all the radiation, a black body absorbs all the radiation that falls on it, and hence it emits all the radiation at those same wavelengths. So a black body at 1200 Kelvin would have a range of emission that looks like this red line at the bottom there. The visible part of the spectrum is shown on the left, ultraviolet on the extreme left, and most of what we're looking at on the left-hand diagram is in the infrared. The wavelength along the bottom, in this case, goes from 0 to 3 microns. Remember that the visible part of the spectrum is less than 1 micron, so most of this is in the infrared. So at 1200 Kelvin, the object is emitting a great deal of energy, and we can see that most of the energy is at that point. Most of the intensity of the light is well inside the infrared part of the spectrum, a little less than 3 microns. If we were to go further down, it doesn't really fit with this diagram, but if we think about your temperature, which is about 300 Kelvin, you will be emitting infrared that peaks at about 10 microns, which is off the right-hand side of this particular diagram. If we bump the temperature up to 1500, two things happen. The curve goes up, in other words, there's more intensity of light, whether it be visible or infrared, coming off this material, and the peak moves to the left-hand side. It moves further and further to the left as the black body temperature goes up and up and up. In order not to go completely off scale, I'm going to adjust the vertical scale to keep this curve reasonably in terms of height. But what is interesting is that as we take the black body temperature up, this curve is going to move further and further to the left. So for instance, if we go to a black body temperature of over 2000 Kelvin, then notice that we are now still broadcasting most of the heat in the infrared part of the spectrum, but notice that the red dot and the blue dot, now tell us that we have some light in the red and the blue part of the visible spectrum. Very little in the blue, most of it appears to be in the red because this particular characteristic blackbody radiation shape, called the Planck curve, is just pushing into the visible part of the spectrum. So any object that's at a couple of thousand Kelvin, we will definitely see it glowing because this curve is now partly in the visible, but there'll be a lot more red than there is blue. So we'll see this as a red-hot object. If we push the blackbody temperature up still further, at 3000 Kelvin, we're now at the temperature of a relatively cool star, a so-called red giant. Notice that most of its output is still in the infrared part of the spectrum, but look at the blue dot and the red dot. Yes, the red giant does emit light across the entire visible spectrum, but there's a huge amount more in the red than there is in the blue. Hence, red giants look red, not surprisingly. If we take the temperature up to the temperature of the surface of the sun, now that blackbody radiation curve is peaking in the visible part of the spectrum. It peaks somewhere around the green. But notice that we've got a finite amount of light coming right across the entire spectrum. We're getting a lot of blue light and green light and red light. We're getting effectively the whole of the visible spectrum radiated by the sun. And that's why the sun looks essentially white. All the colors of the rainbow in slightly different proportions, but essentially all of the colors are represented in the sun, and so an object at this sort of temperature will be glowing white hot. If we take it beyond that to something like 10 or 11,000 Kelvin, now the blackbody radiation has been pushed so far, it's now peaking in the ultraviolet. And when we look at how much is actually in the visible part of the spectrum, we see there's far more blue than there is red. And this sort of temperature, 10,000 Kelvin, is what is labeled an A-type star. It doesn't really matter about the classifications at the moment, but there are certain stars which are generally blue-white. In other words, they are white with a hint of blue. They have a hint of blue because, although all colors are being radiated in the visible spectrum, blue is being radiated more intensely than red. So if the temperature is low enough, we get red giants with lots of red, and so we get red stars. If we push higher temperatures, we don't get green stars, we get stars emitting across the whole spectrum, so we get white. And if we go further, then we get blue stars. So that's why we can get red stars, we can get white stars, and we can get blue stars, but there are no green stars. It's because of the nature of that curve that comes out of the physics understanding of blackbody radiation. If we were to take a whole load of stars and plot their color as a function of how bright they are, this was done many years ago to try and get an understanding of how stars evolve. And that's the so-called Hertzsprung-Russell diagram, hereafter simply called the HR diagram. And if we look at what's going on in this particular area, we see that the colors are down here. Perhaps you can't read them too well, but it's the cool stars on the right at 3,000 Kelvin and hot stars on the left at 10, 20, 30,000 Kelvin. So just like here, it goes from stars that are glowing red and then yellow and then white. It's the same sort of idea on the bottom scale here. For historical reasons, it's plotted cool on the right, hot on the left. That's just the way it was done historically, and they've never flipped the chart over. If we look at where the sun is, there's the sun, and for convenience, we talk about the amount of radiation from the sun, the luminosity, instead of talking about how many watts or how many joules are being radiated, we talk about its luminosity relative to the sun, because that's just a convenient unit to use. So the sun's luminosity is 1, and the sun's surface temperature is close to 6,000 Kelvin. But when we look at trying to understand where stars appear in that particular plot, we find that large stars appear in the top right. These are the so-called giants and supergiants, and small stars tend to be on the left. But also, perhaps more importantly, we find that the large mass stars are in the top left and the small mass stars are in the bottom right. In other words, dwarfs tend to be down in the bottom right, and very massive stars tend to be in the top. So that means if we're interested in, for instance, a star cluster, We can clearly see some of those stars seem to have a little bit of a red tinge, some of those stars seem to have a bit of a blue tinge. But can we actually tell how old that star cluster is just by looking at it and measuring the light from these stars? Given that we can't sit and watch this thing to see what's happening, is there a way of understanding the evolution of that star cluster and how old it might be simply by recording the color and brightness of these stars? That's precisely what Hertzsprung and Russell did in the early days. You can get the color by taking, for instance, a picture of the cluster through a red filter and a picture of the cluster through a blue filter, and the difference in intensity tells you, roughly speaking, what the color of the object is. You don't have to take the full spectrum. And the brightness, given that all of these stars are at essentially the same distance because these are all gravitationally bound into a cluster, so we may not know exactly how far away this cluster is, but all of the stars are at roughly the same distance. So a star that looks brighter than another star is presumably intrinsically brighter. Its luminosity must be higher. It's not simply that it's closer, because these are all at the same distance. So we can take thousands, perhaps even tens of thousands of stars in an image like this and plot all of the stars out in an HR diagram. What we find is they are not scattered randomly all over the entire HR diagram. They tend to line up on this so-called main sequence. Nothing like as regularly as that. This is only supposed to be schematic. Some of the stars will appear in the top right-hand corner, some might appear in the bottom left, but the majority of stars will appear on this so-called main sequence. That's because that's where stars spend most of their lives. Our sun, for instance, will spend something like 10 billion years at its position in that particular part of the main sequence. But if we come back to the idea that we have blue supergiants at the top left and red dwarfs in the bottom right, any star that's very massive is going to have to burn its nuclear fuel very rapidly in order to produce the radiation pressure to stop this star collapsing. If it's very massive, gravity is going to be strong, it'll need to burn its fuel really fast to live. Whereas a red dwarf down in the bottom right here, not much mass, not much gravitational pull trying to compress the star, so the red dwarfs can be much more frugal with their energy production in order to balance the gravity trying to crush the star. So the bottom line is blue supergiants live fast, die young, and red dwarfs live an awfully long time. So that means if we look at the plot of all the stars in the cluster, if we find that the dots go all the way to the top, that must mean that it's a relatively young cluster, because we know that these stars right up here don't live very long, perhaps only a few million years. So the cluster is perhaps no more than 5 million years old if the dots go all the way to the top. But if we find that when we take the picture of a cluster and do this analysis, we find we get essentially the same pattern, but it stops short of going all the way to the top left-hand corner, we can say, well, those stars correspond to roughly this mass, and we would expect stars of this mass to live this long. So we can estimate how old the cluster must be if we're full of stars that only go to that point and no further. And similarly, we can say if it only goes that far, then the cluster must be 100 million years old. If it goes that far, it must be 1 billion. If the number of stars that we find in our cluster only goes as far as the sun, roughly speaking, that's where the sun is at a luminosity of 1 and a temperature of 6,000. If the stars only go as far as the sun, that means all the stars that are heavier than the sun have already died. They've already moved off to some different part of the HR diagram, which I'm not indicating in this particular one. So that means if we only go as far as the sun, the lifetime of the sun, we're about halfway through, the lifetime of the sun will be about 10 billion years or so. So if we find stars all the way up to but no further than the sun, then that cluster must be something like 10 billion years old. So we can actually age what's going on even from a snapshot of a cluster, as long as we've got the color of the stars in the cluster. If we just bring the colors back again for the moment, When we look at the various stars, I mentioned that some stars are quite cool and some stars are quite hot. Well, they've been classified into what looks like a ridiculous sequence. Who came up with that alphabet? They started off trying to classify them alphabetically, then they realized they'd misclassified a lot of things and started shuffling the letters around. So the sequence is by no means alphabetical, but if we take stars corresponding to these various surface temperatures, we find their spectra look very different. The very cool ones, they emit across all wavelengths, but dominated by the red, all the way up to the very hot stars, which again are emitting at all wavelengths, but dominated by the blue. So we can actually tell what type of star we're looking at, either just by looking at its color or by looking at its spectrum and seeing what details are in there. Somebody once asked, well, if we've got all of these stars of various types, what is the average, in the sense of if we added up all of the light from all of the stars in all of the galaxies, what's the average color of the universe? Somebody actually thought, well, rather than just ask the question, why don't we actually work it out? They obviously got far too much time on their hands. So they analyzed the light from 200,000 galaxies, which are relatively local to us. There's maybe a trillion galaxies in the observable universe, so they just took a small-ish number that are within a few billion light years of us. And they worked out, by adding up all the light of all the stars in all those galaxies, what the average color of the universe is. Turns out it's beige, which is about the least interesting color you can possibly have. But they didn't want to call it beige, they just wanted to publish the paper with something more interesting. So they called it either cosmic latte, or my favorite is skyvery. I quite like that as a skyvery color. So I don't know they're going to do anything with this information, but given some people ask, they figured that they really ought to calculate what the average color of the universe is. Let's think of a different class of colorful object in the universe, and that is nebulae. So we know that stars and galaxies are, roughly speaking, just large collections of stars and not much else. So we know that they have continuous spectra. Yes, some stars might be brighter in the red than the blue, some stars might be brighter in the blue than the red, but stars and galaxies effectively have a continuous spectrum. Whereas when we look at clouds of hydrogen and oxygen and other elements in so-called nebulae, we find that they have very discrete emission spectra, in other words, line spectra. They only emit colors of particular wavelengths, not the entire spectrum. And that's a consequence of the atomic nature of the clouds of hydrogen or oxygen or sulfur or whatever it is that make up the nebula. So we might think of an atom as being just a nucleus and a whole load of electrons. That doesn't show us the fact that the electrons are actually arranged in atoms in shells, and the important aspect of these shells is that different electrons have different energy. So it doesn't really matter about the nature of how we choose to represent the atoms. What matters is different electrons have different amount of energy in an atom. And when it comes to the energy in an atom, an electron might be in one particular, we can think of it like an orbit. Strictly speaking, it's not an orbit in the sense of the orbit of the Earth around the Sun, but for this argument, we can think of it in that sort of way. The electron might be at a high energy level and it might want to drop down to a low energy level. If it did, then that jump emits a photon of light, a packet of light with the same energy as the energy lost by the electron. And similarly, if we've got an electron in a low energy level, then an incoming photon of light, an incoming packet of light, can give that electron enough energy to bump it up to the higher energy level. So the bottom line is that if we have an atom with electrons at particular energy levels, there can be absorption or emission of light. The energy of that light must match the energy difference of the two electron states, and that will be atomic specific. In other words, hydrogen atoms don't have the same energy levels as oxygen atoms, don't have the same levels as sulfur atoms. And because energy is related to wavelength, at a particular energy, if we have a packet of light, the energy goes from low to high as we go from red to blue. Notice it's the opposite sense from the wavelength, which goes from low values at blue to large values at red. The important point is that any specific energy has a specific wavelength, has a specific color. So if we have atoms that have electrons with particular energy levels, that means particular atoms will generate light of very specific wavelengths. So every atom actually has more than one energy level, and so electrons can jump between lots of these different energy levels, and so we end up with a light spectrum, which is effectively a fingerprint of that particular atom. We don't have to worry about the details of how we calculate that. That's all the field of quantum mechanics. But any atom that emits or absorbs photons with characteristic patterns of energies, we will find there's a fingerprint, and we will be able to tell that that fingerprint, that set of colors, comes from this atom or that atom or this atom. And if we look at what it is for a lot of nebulae, it just so happens when we look out into the universe, we find there's a lot of hydrogen, not surprisingly. Perhaps it is more surprising to realize that there's a lot of clouds of oxygen out there as well. Hydrogen is fair enough because that's made in the Big Bang. It's perhaps a little more surprising to realize there's an awful lot of oxygen out there. But remember, the spectral colors are on the outside line, and it just so happens that hydrogen emits in the red and the blue, and oxygen emits in the green, or the cyany green color. The wavelengths are there. It's not quite as dramatic as this indicates, because remember, 500 and 486 are actually quite close together in terms of wavelength. They only look like they're well separated here because of the way our eyes are sensitive to those particular colors. This is a supernova that I photographed a little while ago. This is a star that blew itself apart about 10,000 years ago, and what we're looking at here is a huge bubble, if you like, a shock wave of the material that's been produced by this star that blew itself apart a long time ago, and this shock wave has been expanding from the supernova, which was somewhere in the middle. We can't see the star anymore, but the shock wave has been expanding and is now something like 100 light years or so in diameter. If we have a look in detail at what's going on the left-hand shock wave, the color image is on the left, and I've broken it down into what does that look like if we only look at the red and the green and the blue elements of this particular color image taken with a color camera. So the red channel of the color image has picked up the hydrogen, because the hydrogen is emitted here at 656 nanometers and is all picked up by the red part of the camera's optics. With the green and the blue, it's a little different, because despite what that previous diagram indicated, the green and the blue are actually quite close together. The blue of hydrogen and the green of oxygen are not that many nanometers apart, and they both occur where the blue and the green overlap. So in other words, this camera, the sensitivity of the pixels in this camera, will be picking up the oxygen and this particular line from hydrogen. So these two will look very similar, because in a sense they are both picking up the same thing, simply because of where these things happen to sit in the spectrum. It would be really nice if they were separated, but nature doesn't work that way. It's been kind enough to make sure that hydrogen is well distinct from the others. It hasn't been kind enough to make the blue and the green distinct from each other. But it may show up and it may not show up, but if we look in detail at what's going on in the shock wave, we actually see differences between what the hydrogen is doing and what the oxygen is doing, and we can look at certain details. This has been done in excruciating detail by, for instance, the Hubble Space Telescope has imaged this nebula to actually look element by element as to what's the hydrogen doing, what's the oxygen doing, what's the nitrogen doing, etc. There are lots of elements in these supernova shock waves. It tells us something about the supernova to see exactly how they are evolving. It also tells us something about the medium through which that shock wave is traveling, the interstellar medium. So there's a lot of physics to be learned by separating out the colors of particular astronomical objects to see what's going on. But the question is, I guess, why are they different? Nebulae seem to have discrete colors. Because of this process that I've described, atoms have particular energy levels that produces discrete spectra. But we've just seen earlier that a star has effectively a continuous spectrum, which depends not on which atoms are in the star, but the surface temperature. So the spectrum we can expect to get will depend on the atoms if we're looking at a nebula, but it will depend on the temperature if we're looking at a star. But they're both made of the same stuff. Stars are made of hydrogen, nebulae are made of hydrogen. So if we're talking about the same stuff, why do we get drastically different spectra between these two classes of object. It's all down to the density. It's all down to how many atoms are we actually looking at. If the atoms are well separated and not interacting with each other, then we'll get essentially atomic spectra. In other words, we'll get the spectra dictated by the laws of quantum theory. But if all the atoms are so close to each other, they're continually bumping into each other and disturbing each other and perturbing each other and altering each other's energy levels, then all of the lines get smeared out into a continuous spectrum. So the colors we can expect to see from an object will depend on literally just how many atoms there are per cubic centimeter of the thing that we are studying. So if we have a look at that and think about the numbers, how many atoms are there in 1 cubic centimeter of, just to give us perspective, let's start with a lump of metal. It's roughly that number, some horrendously large number of atoms in a lump of copper or lead or iron. It really doesn't make a lot of difference what the metal is. In the Earth's atmosphere, it's still a ridiculously large number. Even though we can move through the air quite happily, we're hardly ever aware of the fact we're moving through a medium in which there are that many atoms per cubic centimeter. If we think of the surface of the sun, you might be surprised to learn that it's a lower number. The number of atoms in the surface of the sun is lower than the number of atoms in the Earth's atmosphere. They're all moving quite fast, they're all quite energetic, but the number of them, the density of them in a given cubic centimeter at the sun's surface is actually lower by a factor of, 1% or something. If we go out to the sun's atmosphere, then it does start petering out quite dramatically. If we look at the corona of the sun, which generally we can only see during an eclipse when the moon covers the disk of the sun, then we find we are getting down to very small numbers, and 10 million is a very small number as far as this is concerned. If we think about the number of atoms in a nebula, the number of atoms in a cubic centimeter is only 10,000 or so. So if we think about a cubic centimeter and a cubic millimeter, we can see that the atoms in a nebula are separated by millimeters. That is a huge distance as far as an atom is concerned. It's not going to bump into the other atoms very often. And that's why in a nebula, each of these atoms behaves as if it's completely ignorant of the fact that there are other atoms around at all. And just to put it in perspective, if we think about what's going on in between the stars, not necessarily in the middle of a nebula, but just in the middle of nowhere, literally between the stars, the interstellar medium might have 1 atom per cubic centimeter. And again, just for perspective, what if we go halfway between here and the next galaxy? The intergalactic medium, okay, not strictly 0, but if we were to take a cubic centimeter of the intergalactic medium, the chances are we wouldn't find anything in there. The density in between galaxies might be 1 atom per cubic meter. So it really should be 10 to the minus 6 there in terms of the number of atoms per cubic centimeter. So what matters is literally how many zeros we have as to what type of spectrum we get. If we have an awful lot of atoms in there, then we're going to get a continuous spectrum because they're all going to be very strongly interacting with each other. If the number is quite small, and 10 million is small as far as we're concerned here, then the spectra will be essentially the sort of spectra that we would expect to get from atoms. There's no hard and fast rule as to when one turns into the other, but these are so different we can quite definitely say the sun's surface is effectively continuous spectrum, whereas nebula are effectively just atomic spectra. And indeed, if you look at the sun's corona, it's effectively just atomic spectra as well. Just because the sun has a continuous spectrum doesn't mean that it's not useful to pick out one wavelength and have a look at the sun at that wavelength. Whoops. Sorry, jumped too far. So we can look at particular wavelengths of the surface of the sun. For instance, there's the sun in the middle there, shown at all wavelengths of light. If we only pick out the wavelength corresponding to calcium atoms that are radiating, we find structures in the surface of the sun. If we pick a different wavelength, we're looking at what the hydrogen is doing. And we're looking at a slightly different height. Given that the sun doesn't have a solid surface, it's a fluid, we're looking at a slightly different height in the so-called photosphere, and hence we're looking at what atoms are doing, and we see different contrast, and we see effectively slices through the atmosphere at different heights by choosing different wavelengths which tell us what different atoms are doing. And we could choose hydrogen, we could choose helium, we could choose calcium. There's an awful lot of elements churning around in the sun. Even though it's mainly hydrogen, there are enough other atoms in there that it's useful to look at other wavelengths to get information about the structure of the surface of the sun. Of course, it tells us nothing about what's going on inside, but it still is useful to look at the surface. So let me finish in the last few minutes just reminding us that spectroscopy can be useful. We don't necessarily just take a picture at one wavelength, at one color. In some cases, it is useful to look at the entire spectrum. For instance, if we've got a planet going around a star, as seen from above, as the planet orbits the star will wobble slightly because they're both moving around their common center of gravity. The bottom left shows you what it would look like if we were looking at this system edge on, in which case the planet will sometimes move away from us, sometimes move towards us, and more importantly, the star will be doing just the opposite. When the planet's moving towards us, the star will be moving away from us, if we have a very simple one star, one planet system. So if we were to look at the spectrum from the star, we generally speaking cannot see the planet. It's much too faint compared to the light from the star. But if we look at the light from the star, we find that the lines from particular elements, doesn't really matter what these elements are, all of the lines will move towards the blue or towards the red, depending on the velocity of the star towards us or away from us as we go through this period. So you can see that the speed of the star relative to us might only change by a few meters per second. And the accuracy with which these so-called Doppler shifts, these shifts towards the red or towards the blue, the accuracy with which they can be measured is now phenomenal. They can now get down to merely centimeters per second. In other words, they can detect whether a star is moving towards or away from us at a speed that is literally just centimeters per second. And so this technique has been used extensively on looking at stars to monitor what the change of particular spectral lines tells us. And if we watch enough periods of this change, we can determine the period of the planet going round the star. So Doppler shifts, very useful because a velocity change of the star gives us a shift, a blue shift or a red shift in the spectrum. Very handy for exoplanet searches. But on a much larger scale, because the universe is expanding, light generally gets redshifted to much longer wavelengths as the light travels through space, where space itself is expanding because of the expansion of the universe. The amount that the light gets shifted compared to its original wavelength is called the redshift. Because the universe is expanding, it's always a redshift for distant objects. And the amount that it's shifted compared to its original wavelength is usually just given the symbol Z. And the redshift allows us to estimate the distance to very remote objects. And just to give us a sort of a yardstick, a redshift of Z equals 1, in other words, if the light gets shifted by the same amount as the original wavelength, that corresponds to a very distant object, which is about 10 billion light years distant. When I photographed this object a few years ago, this may not show up particularly well. I tried to photograph a very distant object at a redshift of 4, this particular quasar that goes under this wonderful name given at the top right there. You might be able to just make out that in monochrome, in other words, when I took the color image and just combined all the colors together, I could just about make out this very remote object. If I tried doing the same thing with color, this is something I didn't do originally but did for this talk. What if I take the original image and break it down so I actually show the original colors? It's very difficult to see the object because it's very faint and it's very red. Because it's been redshifted right out, virtually out of the visible part of the spectrum, it's very difficult to see the color of this particular object. And perhaps it doesn't show up too well in daylight, but if we were to look at the object as a red part of the image, we can just about see that there's a little bit of light there. If we look at green, there's essentially nothing there. In blue, there's absolutely nothing there. So this particular object at a distance of 25 billion light years or so, I wouldn't claim that this is a good way of doing the analysis, but rather than attempting to take the spectrum of this object and saying it's definitely redshifted, what you can do is to say, well, I can see it in the red, I can't really see it in the green, and I can't really see it in the blue, so this object must be really remote because it looks really, really, really red, and I can't see anything in the green and the blue. that might sound like a very weird way of doing not spectroscopy, but a weird way of breaking down the colors. Why wouldn't you just do it properly? Why not just take the spectrum and then you can see whether or not it's redshifted? Well, sometimes you don't have the luxury of taking a spectrum. I didn't have enough photons. It took me 2 hours just to get that tiny little dot there. I could not, and I didn't have the resources to take the spectrum to see what the spectrum looked like. And even big telescopes sometimes do that. For instance, the James Webb Space Telescope sometimes works out a redshift from spectroscopy, but sometimes it works out a redshift photometrically. In other words, by looking at images taken at different wavelengths rather than taking a spectrum. So this is one of the first releases of the James Webb from over a year ago now, and they have done precisely the same thing. They've looked at various galaxies and they've said, well, does that galaxy appear in snapshots taken, the colors above it make it look like red to blue, but remember all of the James Webb is working in the infrared, so that means the long wavelength end of the infrared and the short wavelength end of the infrared. So they're taking lots of pictures at infrared wavelengths, and they're trying to see whether or not the object shows up at all wavelengths or whether it shows up at some and not at others. In the case of the bottom set, for instance, the bottom set with red circles, there's definitely something in the extreme right, red circle, but then you notice as you go further and further to the left, that object seems to disappear. So this object is visible at the very long wavelengths, but disappears at the short wavelengths, just like I found with the quasar that I photographed. And the James Webb sometimes does that because it's much faster to take 1, 2, 3, 4 snapshots than it is to take a spectrum, which might require a much longer integration to get the sort of signal to noise. And they've occasionally fallen foul because, in effect, this idea of taking a photometric redshift is only an approximation to what is actually going on. You can look at this and say, well, it appears redder than it is blue. And from that you can say, I think it's very distant. But they did this, and there were some sensational headlines coming out a few months back saying that they've found galaxies that are so remote they can't possibly have existed in the early universe, so something is fundamentally wrong with all of physics. Well, no, it's because they did photometric estimates of the redshift, because that is faster. They then went back at a later date and did proper spectroscopy, and then found that it didn't quite agree, and these galaxies aren't actually quite as far away as they first thought, so it's not breaking any particular bit of physics. It's just that some people pick up on the headlines and they don't read things like the tentative analysis, the provisional analysis, the candidate for this galaxy. But basically it is perfectly reasonable to take snapshots and look at whether or not the object is visible at different wavelengths rather than taking a full spectrum, if that's the quicker thing to do. A question I often get in all of these talks is, I've seen some wonderful images from the Hubble Space Telescope. Are they true colors? When we look at the pillars of creation here on the right-hand side from the Eagle Nebula, the colors look absolutely fantastic. Are they real colors? And in this case, the answer is no. Because what they've done here, they've broken the image down to red, green, and blue, but this wasn't taken with a red filter, a green filter, and a blue filter. It was taken at 3 very specific wavelengths in the spectrum, which they thought would be interesting based on the molecules that are present in this particular nebula. In other words, they've imaged at a particular wavelength corresponding to sulfur, a different wavelength corresponding to hydrogen, and a third wavelength corresponding to oxygen, indicated there. And then they've taken the image produced by sulfur and said, let's make that red. The image produced by hydrogen, they've said, let's make that green. And the image produced by oxygen and said, let's make that blue. They have kept them in order, you notice. From the long wavelength to the short wavelength, they've kept them in the order they were taken. But although oxygen is bluish and sulfur is reddish, there's no way that hydrogen glows green. But you have to give it a different color, so they've opted to make hydrogen green. So no, this is not the true color. This would not be what it looks like if you were standing in front of it. But they've done the best they can by taking 3 wavelengths and keeping them in order to map them onto the red, green, and blue. And of course, you have to do the same thing if you're not working in the visible part of the spectrum. Some people expressed some disappointment when the James Webb Space Telescope was launched because they said, well, it works in the infrared. So when it generates the images, we won't be able to see them because they're infrared and our eyes aren't sensitive to infrared. So any picture that James Webb produces is going to look black. Well, no, because you can do exactly the same thing. You can decide to take images at any wavelength you like and arbitrarily assign them to any three colors you like. So even when you decide to go beyond the visible part of the spectrum and decide to take images in X-ray or ultraviolet or infrared or microwave, not so much in the radio wave, but certainly in the UV and the infrared, you can choose to do pretty much what you like. The James Webb Space Telescope has a whole load of filters in more than one filter wheel, and it can choose to let through light of either a relatively wide bandwidth or a relatively narrow bandwidth. It has lots of filters available to it, as shown schematically in the bottom left there. I know you can't read the scale, but the visible part of the spectrum is actually right on the left-hand edge of this. In other words, even though they are colored differently, they are all infrared wavelengths. And sometimes when you look at some of the James Webb output, if you go onto the James Webb NASA web pages, if you excuse the pun, you find lots of information about what it's doing and what it's trying to image. Sometimes it says explicitly, here's a picture of what's going on around the star at 1.8 microns. Here's a picture of what's going on at 2 microns. Here's a picture of what's going on at 3 microns, explaining that, in this case, the blue is telling us what hydrogen is doing, the green is telling us what molecular hydrogen is doing, and the red is telling us what the dust is doing. That matters because atomic hydrogen and molecular hydrogen act differently when you're making a star, so it's rather important to understand the difference. So sometimes a James Webb picture will explicitly say, here's pictures taken at different wavelengths. But at other times, it simply gives you a color image where they have combined this infrared wavelength and that infrared wavelength and this infrared wavelength and produced a color image. But if you're interested, the data is always available. It's a little bit difficult to see here, but if you look in the bottom corner, it tells you that, for instance, there was the green of this is being assigned to the 2 micron, and there's a letter after it. W means wideband. So a 2 micron wideband filter was used to generate the green, and the red was a 3 micron medium band filter. They tell you which filters were used and which colors have been assigned in order to generate the image you're looking at. So most people don't care. They just want to look at the pretty pictures and say, wow, that's an interesting looking nebula. But if you are interested, you can actually backtrack from the information that NASA gives you to tell you these wavelengths have been mapped to these colors. And of course, with infrared, there's no particular reason why there's any relationship between them. But wherever possible, you can't read this here, but wherever possible, they do keep the order the same. In other words, the blue of this image is the shorter wavelengths. The red in this image is the longer wavelengths. So you can interpret these images by looking at the legend provided by the James Webb Space Telescope images. So the take-home messages for this talk is the eye is not a camera. It does not simply detect color intensities and feed those signals to the brain. It is far more complex than that, and the eye and the brain between them do a huge amount of processing, which means you can't always get to the root of what is it I'm looking at. And you can easily be fooled into looking at colors that either you can't see, or colors that you think aren't there, or colors that aren't there that you think you can't see. The colors of stars are determined by the physics of blackbody radiation, and they range from red to white to blue. There are no green stars because in the middle there, all colors of the visible spectrum are represented, like, for instance, in our whitish sun. In the colors of nebula, the atoms are so far apart they don't interact with each other, and so the colors are determined by the quantum jumps in their constituent atoms, because the atoms are not interacting with their neighbors, so it's effectively just atomic spectra. And if we break the light of any object down into a spectrum, it can be enormously useful, because that will allow us to measure, for instance, velocities and distances to various astronomical objects. So those, if you like, are the take-home messages behind color in the cosmos. Thank you all for listening.